Okay, so this is your DNA sequence, and let's say I want to amplify from here to, let's say, up to here. Okay, so to do that, I have to design two primer, forward and reverse. Now making this forward primer is actually very easy. Just write the way it is, like AG, AT, GA, TT, AA, TT, AG. Just write it the way it is from the sequence from 5' to 3' direction, and here you make your forward primer. So this direction from 5' to 3' is actually very important. Now making reverse primer is actually a bit tricky. Let's say I want to focus on this area to design my reverse primer. So this is the sequence TC, GG, CG, AC, TT, GA, right? And let's say I want to design my primer, but let's find out the complementary sequence to it. A, G, G, C, C, G, C, T, G, A, C, T. Now the direction 5' to 3'. So this is your reverse primer. Okay. If you go here, you can see the same sequence here I have written TC, AA, GT, CG, CC, GGA from 5' to 3' direction, and this is your reverse primer. So this is your reverse primer when written from 5' to 3' direction. Now this direction from 5' to 3' is very important. Every time you write a primer, you should always write it from 5' to 3' direction, whether it is your forward or reverse primer, and this point is actually very important. Now remember, this example is just a very simplified and a very rough example. In ideal, the length of the primer should be around 18 to 30 nucleotides, whereas 20 is considered to be the most optimum. Now, GC content should be between 40 to 60%. Sometimes you can keep it 30, but do not go beyond that. And also try not to go beyond 60%. Because what happens if you use too low, then the binding will be very, very weak. And sometimes if you use too high, then it can cause non-specific binding. Similarly, the melting temperature between the two primers, they should never be more than 5 degrees centigrade. And the melting temperature of your sequence or of the product, they should not differ from the melting temperature of the primers by 10 degrees centigrade. Now you can calculate the melting temperature of your product using this formula. You can see how many G and C base pairs are there, how many AT base pairs are there, and then you can calculate the Tm. Now another very important point to keep in mind that you should try not to use sequences like this G G G G G G G or too many repeats like AT 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 AT, because what happens, your DNA polymerase, they sometimes slips. They get confused. They think they have copied, whereas in real they actually didn't. Or sometimes they actually copy one portion multiple times, and that can cause error. Then another very important point to keep in mind, that you should try not to choose primers which are got this kind of sequence, that is self-complementary. Let's say this sequence and this sequence, they are complement to each other. So what happens? They will form hairpin loop. The primer, they actually fold back on itself. As you can see here, they are folding back on itself, and then they are forming this hairpin structure. And once this hairpin structure is formed, the PCR efficiency will reduce. Now, not only self primer, sometimes what happens when the forward and the reverse primer, they are very much complementary. That is, the sequences are very much complementary, then they will cause primer dimer. As a result, what happens? Instead of binding to DNA, the primers, they bind to each other, and the actual reaction they lose efficiency. Sometimes during qPCR, they produce false signal which will make your data extremely unreliable. And since those bands are very small, therefore the DNA polymerase will amplify them fast, which will give extra unwanted bands that might confuse you with the real bands. So every time try to generate clean primers that will make your life way easier in your lab. Now here is a very real life example. Now this is our DNA sequence, uh, and now if I go to this software called Primer3, which we normally use in lab to design primers, you just put the sequence here. Then if you want, you can check your requirements, the primer size from 18 to 23 up to 120 as I've said, the melting temperature 57 to 59, max CM difference is 5. You can see here they're using GC30, you can make it 40 if you want, max 60, and after setting everything you can go and you can just click pick primers, and then this software will generate primers for you automatically. As you can see here, this is your forward primer and this is your reverse. Now you can see there is no hairpin 0 or no primer dimer or any self complementary. So this is a very good generation, I must say. Now if you want to know from which portion they got the primer, here is the sequence given: 1364 your forward primer and 1533 your reverse primer. Your forward primer TGC TGGA, so you can just go down and here you can see it is TGC TGGA, and this is your forward primer, and then your reverse primer is they took it from here. So you know how to do it. TTAA, so check for their complementary sequences like AA, TTT, CCC. Now just go there, go up and see the sequences will be like this. Here it is AA, TTT, CCC, and here see this is your reverse primer. So this is how you design your primers. It's very simple. There is nothing too difficult. Forward primer exactly just the way it is, and reverse primer just see the sequence, just take their complementary sequences and then write it from 5' to 3' direction, and there you will get your both the primers. That's all for today. Thank you.